As our final result in discussing the Planck distribution and electromagnetic wave production, let's imagine that we've got some solid object here whose atoms and molecules are in thermal equilibrium at temperature T. Well, as we've been discussing, that implies that there's electromagnetic radiation that they're also in thermal equilibrium with. All right? Now, if I'm just looking inside the body of this object, that radiation is just there. But not so if I look at a little portion of the surface. If I'm looking at a small surface area, ds, and let's actually make it a surface element so that it points normal to this little piece of surface. Any electromagnetic radiation that is going in the right direction and is close enough to the surface will escape my object. All right, so I can ask, how much radiation do I get? All right, well, let's see. Unlike what we've been doing, here we can't do it isotropically. Here the direction matters. If I have a little piece of radiation going that way, it's not going to escape. I need the radiation to be going in the correct direction. Needs to go out like that. All right? So that means that I can't integrate the direction out. Remember, that's what we've been doing? That's where we got this 4 pi nu squared d nu. I can't integrate that out. I got to go back to the more primordial expression. 2 this part is just going to hang around for the ride. All right? So I'm going to leave that in terms of frequency because this part is isotropic. The probability, well, the amount of energy given to an electromagnetic wave doesn't depend on what direction the wave is going in. All right? But this part, I have to be careful with. All right? I want my wave number to be going the right way. Okay? So we've got our normal here. I'm going to take that as the k-hat direction. That's going to be our normal. And my k vector has got to be coming like that. It doesn't matter what its I hat and j hat components are. All right? We say that there's an azimuthal symmetry about the n hat direction. That doesn't matter. But the k hat, the direction associated with the normal vector here, that does matter. That's got to be positive. So I'm going to view that with angle Now, in physics, we would usually call it angle theta, but because of the multi-book that we use, it's angle phi, all right, in multivariable calculus. So let's just leave it at that. All right, I need phi to go only from 0 to pi over 2, not from 0 to pi, because I don't want it to be going in the wrong direction. It has to get out. All right? Now remember, this was energy density. Energy density. Energy per unit volume. So I want to know how much energy total gets out. So I have to multiply by a volume. Okay? So what is that volume going to be? Well, I'm going to have this ds vector, right? That's the surface area. And then I want the light to be close enough to get out in a short amount of time, delta t. So how close does it have to be? Well, in the short time, delta t, light will go the distance c delta t. But in this direction, it's only going to go c cosine phi delta t. All right? Because this radiation is not going directly out. It's going sort of at an angle. So I need it to be close enough so that its z component of velocity will get it to the surface in that short time delta t. So this is going to be c cosine phi delta t. And this is the energy that escapes in time delta t. All right, so let's see what we got when we integrate this. Remember, I'm not being azimuthally symmetric. So I'm going to integrate. I've got 2 2c. And now I want to integrate over my angles. Let's just do the angular integration and leave this stuff out. This has to do with the angular integration. So I'll go 0 to pi over 2 sine phi d phi. 0 to 2 pi d theta. And then I'll have cosine phi. This is the angular integration. All right? The theta integral obviously gives me 2 pi. The phi integral I could do a u substitution. U equals sine phi. So this would be 2 pi integral 0 to 1 u du, which is pi. All right? Now remember, when we did the isotropic calculation where we integrate over the whole sphere, we would get 4 pi for the angular integration. Here we're only getting pi. So it's effectively 1/4. All right? All right. At any rate, that all goes through. I still have to multiply it by k squared. That's like if you were in multivariable calculus, remember the volume element was rho squared d rho sine phi d theta. That's what we just did. I still need the rho squared, and that's going to be k squared. All right, because the vector has magnitude k. So I'll have 2 integral 0 to infinity. I'll have h nu divided by e to the beta h nu minus 1. This is going to give me pi k squared dk divided by 2 pi all cubed. And then I'll get my ds c of delta t. Cosine t integrated out with the angular integration. Now, remember that k is 2 pi over lambda. So that's 2 pi over c times the frequency. So this 2 pi over c, that's why when I write it in terms of the frequency, I have c cubed instead of 2 pi cubed. All right, so this is going to be all right. Now, if you compare this to what we got for the total energy density, you'll find that it's just total times c over 4 times the area of the little piece of surface times the time interval that I want to wait. Of course, if we divide this by delta t and we integrate over the whole surface area, we get this sort of interesting result. The total power I feel like that only has, oh, all right. The total power emitted is equal to, well, it's going to be oh, sorry. I already did the 1/4 because it was 8. All right, we get that. So that's going to be equal to pi to the fifth k Boltzmann to the fourth divided by 15 h cubed c squared. A t to the fourth. Now let's see what that gives numerically. See if anybody recognizes this number. Okay, so I've got 2 pi to the fifth k Boltzmann to the fourth divided by 15 h to the third c squared. All right, and let's see what that is. 5.67 times 10 to the minus 8. Huh. So that, of course, is the Stefan Boltzmann constant. All right? It comes directly from this analysis.